All right, so this whole time we've been talking about ideal gases. Of course, in the real world, gases aren't ideal. So remember what we said about ideal gases. We said that the particles essentially have no volume, right? That their volume is negligible, and that there's no attraction between any of these molecules, right? All of the collisions are completely elastic, and the molecules don't, have any sort of preference to go close to one another. Neither of those are true. They are approximately true under normal conditions, but not totally true, right? Real gases, they do have volume, right? They're made out of molecules. The bigger the molecule, the bigger the volume it occupies. The other thing about gases is that they are attracted to one another. We'll learn about this later. These are called IMFs, or intermolecular forces, and we'll learn about them later. But the end of this, the gist is that molecules do attract one another, and they do prefer to be in contact with one another. So remember, under normal conditions, real gases behave approximately ideally. And normal conditions mean like low pressures and high temperatures. High temperatures you might not think of like as a kind of normal conditions, but if you think about 0 degrees Celsius, that's equal to 273.15 Kelvin. So even at 0 degrees Celsius, you are still at, a relatively high temperature. So under normal conditions, gases will behave ideally. As we get away from normal conditions and get to more extreme conditions, the gases behave less and less ideally. So when don't they behave ideally? They generally don't behave ideally when we have high pressure situations or and low temperature situations. Under high pressure situations, the molecules start coming into contact with one another. There's less empty space between them, and so they occupy a non-negligible amount of volume, right? So gases occupy more volume than the ideal gas law would have you predict. And that's because, according to the ideal gas law, right, they don't occupy pretty much any volume. And then also at low temperatures, when the molecules are at low temperatures, they're moving very slowly. And so when they come in contact with one another, they can really stick to one another because they are attracted to one another. And so what if our ideal gas law isn't good enough? Well, we can use more advanced equations. So for example, our ideal gas law, PV equals nRT, it's great because it's simple, but it's not as accurate as some other equations, and it might not be accurate enough for whatever purpose you're using it for. So you can use a more complex equation, such as the van der Waals equation, which looks like this. Right, so you can tell it has pretty much the same variables as our PV equals nRT, right? It's got P, it's got V, it's got N, it's got R, it's got T. It's got some additional ones, right? It's got this A, and this overall expression is, lacking from the PV equals nRT. And this is what's known as a correction. And this one is for molecular attraction. And then same thing, this B right here, and really this minus NB is a correction for the volume of the molecule. And there are other advanced equations out there. The downside is, right, they're more complex equations, and it's harder to use, right? So you have to think about what kind of scenario you're dealing with and how exact you need to be, right? So as scientists, we're always building models of the world, and so we always need to ask ourselves is, how accurate of a model do you need to get a good enough answer, right? Getting an exact answer is extremely, extremely difficult, even for very mundane measurements or questions. And so oftentimes it's not a question of getting the exact right answer. It's about being close enough for whatever purpose you're looking at. Cool. And that's it about gases.